This is the second video about this problem set, function composition problem set. And I wanted to talk about the third and final page a little bit and give you some directions here. Notice the directions say to complete this table and use your graphing utility to investigate the domain, the range, and the invertibility. So let's just focus on the first column here, function family. And this maybe is a new way of thinking about our functions that we've been studying, but it's not that hard. I'll give you some examples of function families. We have linear functions, and we have quadratic functions, and we have cubic functions. And all of those together are examples of polynomial functions. So here are 4 function families. We like to be as specific as possible. So we wouldn't just say polynomial if we knew that a function was actually linear. We'd say linear. Let me label this here, function families. There are some other function families that are not polynomials, like exponential functions. We've studied those, and we've studied logarithmic functions. I've also studied rational functions. A rational function is the ratio of 2 polynomials, a fraction, in other words, with a polynomial on top and a polynomial on bottom. And what other kind of functions have we studied? Maybe radical functions, like anything with a square root or a cube root or any kind of root. Those are radical functions. And there's some other functions that we haven't studied yet that actually don't appear on this problem set, but we have trigonometric functions, for example. There's a function related to the exponential function called the logistical function. So there's a lot of different function families, and the idea here is to start recognizing when we're looking at an equation, in this case, what type of function we have or what family these functions belong to. And also we want to be able to look at a graph and understand what family that function belongs to. So in this task, this first function, maybe you can see it's just a linear function because this is the equation of a line. So I just put linear here. And I'll just let you go down and do the other ones. And notice what's happening here and from here down on this problem set is you don't know what function family those are going to be until you actually go through with whatever operation is dictated by the left-hand side of the equation that has been given. And maybe a useful resource to you in this task would be this frame about functions that we constructed in class together. And there is a slideshow about this frame on PowerSchool Learning. And I'll just draw your attention to this last section. We have a couple of functions, f of x and g of x, and we learned how to combine these functions using addition, subtraction, multiplication, and division. And here are some examples of how we took these 2 functions, f of x and g of x, and engaged in these different combinations. We also learned about function composition, where f of g of x, which we could also write this way, and that's maybe a more familiar way of writing it from this problem set. We can compose these 2 functions to get a new function. And really, that's what you have to do on this problem set for these remaining 6 or 7 rows. So just to do an easy one together real quick, f plus g of x is really the sum of these 2 functions, f of x and g of x. And so I'm really just going to add up the 4 terms that I see here, and I will put the result in standard form. So I'm going to start with my negative x squared, and I'm going to add 2x, and plus 1 minus 3, that's minus 2. So that is the combination using addition of these 2 functions f and g. It's just f of x plus g of x written in standard form. So when we compose functions, it's a little different. We're not actually doing a mathematical operation necessarily, but instead, in this case, we're taking the entire function k and we're substituting it into h wherever there's an x. So here, h of x is equal to 1 over x, and k of x is equal to the square root of x plus 4. So I'm just going to take this entire thing right here and just substitute it in for x, and that looks like this, like that. So you have to divide functions and maybe compose a couple of different functions, and this is an inverse function. When we find f inverse of x, and this is the notation for an inverse function, what we're looking for is the function that undoes whatever we do to x here. And again, we had a lesson about this, and I'll just remind you how we undo this process. So let me start with f of x equals 2x plus 1. That's the function f. And in order to invert this function, remember what it means to have the inverse of a function is here we put x in, we put a value in for x, and we get a value out for y. And we want the function where I could take that value of y, put it into my new function, and it would return back the same value of x that I started with. So my first step in finding the inverse function is just to substitute y for the name of the function. And this just helps me manipulate this equation a little more easily. And so this is basically given. So the next step is just to switch the x and the y in the equation. Wherever there's an x, I'm going to put a y, and wherever there's a y, I'm going to put an x. So we switch x and y to find the inverse. And now let's solve this for y. First, let me subtract 1 from both sides of the equation. X minus 1 equals 2y. And so I've just used the subtractive property of equality to do that. And then I just need to divide both sides of this equation by 2 to get the y by itself. And I'm going to just rewrite my problem with the y on the left-hand side. It's x minus 1 over 2. And that is the division property of equality that makes that possible. So that is my inverse function. And I'm going to put that right here. And so that's what you have to do in order to find these other inverse functions as well. Don't be afraid to pull out a piece of scratch paper and work it out there. Once you've figured out the equation for all of these functions, then you can graph them. And that is an easy way to, or maybe it makes it easier to see if what the domain and the range are, and how, if there's anything that you want to, any way that you want to restrict the domain or range for each of these functions. And then the last column here talks about whether or not a function is one-to-one. And again, we go back here real quick, and we're reminded that we can use the horizontal line test to see if a function is one-to-one and therefore invertible without restriction. In other words, can you find the inverse of this function without having to constrain the domain and range? And we basically just, if you can draw a horizontal line that hits your graph at more than one place, then your function is not one-to-one. If you can draw a line, if there's no way to draw a line that hits your graph in more than one place, then your function is one-to-one. And that's how you answer these questions here.